Thank you very much, Song, for your introduction. So let me share my screen. Okay, hello everyone. I'm Liu Kang from Shenzhen Institute of Advanced Technology, Chinese Academy of Sciences. I'm very glad to have such opportunity to share our recent work. Many thanks to all the organizers of the webinar. And today I will introduce our recent work titled Knowledge-Driven GeoAI Models for Human Trajectory Generation. So spatial temporal trajectories of individuals have significant implications for many applications, such as transportation management, epidemic simulation, crowd gathering warning, urban planning, and so forth. For instance, simulating the movement patterns of suspects and residents can aid in identifying hotspots of criminal incidents, thereby reducing the crime rates. Integrating individual movement process to construct spatially explicit disease transmission models has become a cutting-edge technique for epidemic prediction and control strategy simulation. The rapid development of information and communication technologies in recent years has facilitated the collection of large-scale human mobility data, including the GNSS traces, mobile phone recalls, smart card data, social media check-ins, and so forth. Thanks to those data, lots of great research has been done in recent years. However, despite the wide collection of individual trajectory data, its availability is still greatly limited due to concerns regarding personal privacy. Moreover, the raw data usually have issues of data redundancy, data missing, and data noise, which severely affect the usability of the data. So against this background, establishing models to generate synthetic trajectories that are statistically close to the real data without recycling real information is a promising solution. It is worth to mention that synthetic data has received increasing attention in a broad context in recent years. A recent Nature Outlook article titled "Synthetic Data Could Be Better Than Real Data" emphasized the great potential of machine-generated datasets in privacy protection and addressing data bias. This article advocates for researchers and the public to embrace and accept the data generation technology and its impact. So back to the topic of synthetic trajectory generation. Existing trajectory generation methods can be divided into two categories: mechanistic models and machine learning models. Mechanistic models are mainly started by researchers in the field of statistical physics. They establish models to simulate individual mobility process so as to explain the potential mechanisms behind the statistical regularities detected from massive real data. The most classic mechanistic models are the exploration and preferential return model, the EPR model and its variants. The machine learning-based trajectory generation models are mainly based on recurrent neural network, attention mechanism, generative adversarial network, variational autoencoder, and diffusion models. And we can see that many studies on mechanistic models have been published on top comprehensive journals such as Nature Human Behavior, while the machine learning-based models were mainly published on top conferences of computer science, such as IGCAI, CPGIS, AAAI, and so forth. This table shows the pros and cons of the two types of models. The main advantage of mechanistic models lies in their high interpretability, low requirement for training data, strong generalization ability, and few parameters. However, existing mechanistic models are still insufficient in depicting the individual's complex mobility behavior, which results in significant disparities between the generated and the real trajectories. The main advantage of machine learning models is that the generated trajectories tend to closely approximate the real ones because they can effectively learn the complex and implicit human mobility behavior from the data. However, machine learning methods usually need large-scale training data and the lack of interpretability due to their black box nature. Although the two types of models have existed for many years, they are still developing independently within their respective domains without integration and complementation. So here we are interested in how to adaptively combine and leverage the strengths of both machine learning and mechanistic models. Currently, scholars from different fields have proposed or summarized some coupling ways of data-driven and knowledge-driven models. However, as the form of mechanistic models vary widely in different fields, it is difficult to directly apply the coupling ideas from other fields to the problem of trajectory generation. So we firstly designed a coupling paradigm framework for trajectory generation. The framework includes four coupling ways. We designed 4 coupling ways. The first one is the mechanism and learning cascading model. In this design, mechanistic model and machine learning model are applied in different stages of the trajectory generation. For example, the machine learning models can be used to generate the temporal patterns of human daily activities, while the mechanistic model can be used for spatial selection. The second one is mechanism and learning paralleling model. In this design, mechanistic model and the machine learning model can be used as a trajectory generation model separately and combined equally. The third one is mechanism-guided learning model. In this design, machine learning is used as the main model for trajectory generation, which is guided by mechanism. For example, we can design space-time constraint laws for the machine learning model. And the fourth one is learning embedded mechanistic model. In this design, mechanistic model is used as the main model for trajectory generation, while machine learning models can be used for parameter update or act as an agent of a submodel. So today I will introduce our proposed trajectory generation methods based on the first and the third coupling paradigms. And the first one is called activity to location method. The method consists of 2 cascading models, the activity sequence generation model and the spatial location selection model. The former is constructed based on machine learning models to generate activity sequences for a given number of individuals that consist with the temporal patterns of human daily activities, while the latter is established based on mechanistic models to explicitly determine specific locations of the activities in each generated sequence. So this way, a given number of synthetic trajectories can be generated. Only small sample real activity sequence data and population distribution data are used in the method, so it is a low-cost input. Before introducing the methodology, I would first introduce the data and the evaluation metrics used in the study. We selected Shenzhen City, China as a study area and divided it into spatial units of 1 kilometer grids. 2 data sets are used in the study. The population data were derived from the word pop and aggregated into the 1 kilometer grids. The mobile positioning data was sourced from a telecommunication operator, China Unicom, including trajectories of 200,000 individuals of 1 week in November 2021. After pre-processing, each trajectory can be represented as a sequence of grid IDs with equal time interval We used 1 hour in our study, so the length of the sequence is 168. Furthermore, we extracted activity types from the trajectories and constructed activity sequences for individuals. It is easy to detect the home and work types by rows from the trajectories, but difficult to identify other activity types such as shopping and recreation. So we labeled them as other. Different other activity locations of the same individual were labeled as other 1, other 2, which can reflect the relative richness of different individuals' daily activities. For the evaluation matrix, we selected several metrics to depict the spatial temporal characteristics of a trajectory dataset, and used a JSON channel, the GIS divergence, to evaluate the difference between the real and the synthetic trajectory data. Specifically, duration indicates the time spent at the same location by an individual. Displacement indicates the distance between 2 consecutive distinct locations visited by an individual. Log number indicates the number of distinct locations visited by an individual. Radius indicates the radius of gyration, a feature distance around the centroid of an individual's trajectory. I rank indicates the visiting frequencies of top 10 locations, sorting in descending order with respect to an individual. And G rank indicates the visiting frequencies of top 100 locations, sorting in descending order with respect to all individuals. And we also applied the common part of commuters, the CPC metric, to measure the similarity of mobility flows between locations that were aggregated from the synthetic and the real trajectories. Here comes to the details of the methodology. In the first step, we constructed the individual activity sequence generation model. We know that a transformer, a recurrent neural network, and its variants such as LSTM, GRU, have been proven effective in sequence modeling and time series forecasting. However, when they are globally trained across all available but heterogeneous sequences, the overall accuracy may degenerate. Existing studies have proven that prior subgrouping of time series is able to improve the performance of the baseline models. Considering that human daily activities often exhibit regular routines or temporal patterns, such as stay at home all day, homework home, homework recreation home, we adopt a similar idea for generating individual activity sequences. Firstly, we clustered the individual activity sequence data using K-Meadows algorithm. So this way, activity sequences in the same cluster would have the similar temporal pattern. Then for activity sequences in each cluster, we trained a transformer as the individual activity sequence generation model specifically for that temporal pattern. Using those trained transformers, we can generate a given number of new individual activity sequences aligning with the corresponding temporal patterns in the real data. Then we determine the locations for activity types in each generated activity sequence based on mechanistic models. Firstly, we selected the location for home type. All individual activity sequences contain the home type. The probability of a location being selected as an individual's home location is calculated as the ratio of its population to the total population. Then we select locations for work and other types. The transition probability of an individual to move from one location to another can be calculated by many mechanistic human mobility models, such as a gravity model, radiation model, intervening opportunity model, and so on. Among those models, we choose the universal opportunity model published in scientific reports in 2020 to calculate the probability of an individual at location I choosing location J. The new universal opportunity model is an intervening opportunity-based model that have been proven to have better performance in predicting human mobility at different spatial temporal scales. The basic rule of this model is that when individuals choose a destination, they will first evaluate the opportunity benefits that all locations will bring to them, and then comprehensively compare the opportunity benefits of the origin, the destination, and the intervening opportunities between the origin and the destination. For work location selection, the origin indicates the home location, while for other activity location selection, the origin is its previous location. There are two parameters in the model. Alpha indicates the preference for high benefit, which is population in our study, while beta indicates the preference for short distance. We fitted the parameters using real flow data in the study area, and we can see that beta is larger than alpha, indicating that residents have a greater preference for short distance than for high benefits in both situations. And this phenomenon is particularly significant in the selection of other activity locations, which is consistent with our notion that individuals usually have less flexibility in choosing a nearer workplace and have limited time budget for conducting other activities at a distant place. We compared the activity sequence generation models with and without prior clustering by k-methods. In addition to transformer utilized in our method, we also selected RNN, LSTM, and GRU as a comparison. Each model generated 50,000 synthetic activity sequences trained on the 50,000 real activity sequences by a sequence-to-sequence scheme. We applied the bilingual evaluation understudy metric, the BLUE metric, to evaluate the similarity between the generated and the real sequences. BLUE is initially proposed for evaluating the quality of text sequence, which has been machine translated from one natural language to another. It computes the n-gram overlap between two sequences. So from the table, we can see that all sequence generation models with prior clustering outperformed those without prior clustering. This is because the clustering then generation strategy can avoid the dampening effect caused by heterogeneous data training in the same model and help preserve the original temporal patterns. And moreover, we can see that the transformer behaves an excellent performance even without prior clustering, proving the suitability of transformer in modeling human mobility sequences. So the left figure shows the clustering results of real activity sequences of the 50,000 individuals. The optimal number of clusters is 8, and 4 significant patterns can be identified. The first one is a homestay pattern, indicating that individuals' daily activities are dominated by home type. This pattern accounts for about 60%. We also have 3 other working patterns, but with different working hours. For example, the 996 working pattern indicates that individuals' activities from Monday to Saturday, starting at 9 a.m. and ending at 9 p.m., are dominated by work type. This pattern accounts for about 10%. And we also have a 995 working pattern and a 965 working pattern. We can notice that the homestay pattern accounts for a large proportion, about 60%. This is because activity types in our study were identified from the raw trajectories. If an individual's workplace is in the same spatial unit as her home, it will be identified as home type. But this would not make a difference on the trajectory generation result based on our proposed spatial location selection model. As for the evaluation of the generated trajectories, this table presents the GIS divergence toward the 5 spatial temporal metrics and the CPC metric. Our proposed method outperforms the baselines in all metrics with the lowest GIS divergence and the highest CPC, indicating that it can generate synthetic trajectories aligning closely with the real data. Specifically, we can see that duration, log number, and I-rank metrics are mainly determined by the activity sequence generation model, reflecting that transformer with prior clustering can help capture and preserve the temporal patterns of the real data. While the good performance of space-related metrics such as radius and displacement and CPC reflects the effectiveness of our proposed spatial location selection model in reproducing the spatial distribution of the real data. From those results, we can see that the combination of machine learning and mechanistic models can achieve better performance than using machine learning or mechanistic models alone. And both types of models in our activity to location method have leveraged their strengths at the right places. To test the effectiveness of different mechanistic models in spatial location selection model, we also substitute the universal opportunity model with other mechanistic models for selecting work and other activity locations. 4 classic models are utilized for substitution and comparison, including gravity model, rank-based model, radiation model, and the opportunity priority selection model, the OPS model. It is worth to mention that the radiation model and the OPS model are covered by the UO model using its 2 parameters, alpha and beta. When alpha equals to 0 and beta equals to 1, the universal opportunity model is equivalent to the radiation model. When alpha equals to 1 and beta equals to 0, the universal model or the universal opportunity model is equivalent to the OPS model. And we can see that metrics such as duration, log number, and I-rank seem not to be related to the choice of mechanistic models. This is because those metrics mainly depict the temporal patterns of trajectories, which have been constrained after the activity sequence generation phase. As for the space-related metrics such as radius, displacement, and CPC, the universal opportunity model exhibits the best performance than other mechanistic models, indicating that it can better reproduce the spatial distributions of the real human mobility behavior. Here we show a figure. The figure shows 4 generated individual trajectories of a week under the 4 activity patterns. To conveniently compare the trajectories, we selected individuals with the same home location and work location if they have. The first figure shows an individual trajectory without a workplace outside the home location. In such a situation, the other activity locations are mainly concentrated around the home location, which reflects the constraint effect of the residence. And the figure B, C, and D show individuals who commute between their homes and workplaces, but with different working hours. Individuals with longer working hours tend to have fewer and closer other activity locations. This is because activities of home and work dominate human daily life, and individuals with a busy work usually have limited time budget to conduct other activities at a distant place. This is consistent with our common sense. So here comes to the summarization of the first method, the activity to location method for trajectory generation. Firstly, an activity sequence generation model was constructed using two machine learning models, K-models and transformer, to generate individual activity sequences based on clusters of real activity sequence data, which can help capture and preserve the temporal patterns of human daily activities. Secondly, a spatial location selection model was established using mechanistic models to explicitly determine specific locations of activities in each generated sequence, which can enable the capture of spatial distribution of human mobility behavior. Thirdly, our proposed activity to location method was comprehensively evaluated, and the results demonstrated that proposed method outperforms other trajectory generation methods based on purely machine learning models or mechanistic models, as it adaptively combines and leverages the strengths of both. And lastly, the proposed method can generate a given number of synthetic trajectories using only small sample activity sequence data and population distribution data, with low data requirements and ease of implementation. Next, let me introduce another trajectory generation method we call it trajectory generation GAN. This is a typical mechanism-guided learning model. In this work, we designed a space-time constrained generative adversarial network for trajectory generation. And in this design, GAN is used as the main model for trajectory generation, which is guided by mechanisms, that is the space-time constrained generation task and training laws. I would like to introduce the data format first. Instead of 1 kilometer grids used in the former study, here we used two types of spatial units, street, 街道, and community, 社区. Both are administrative divisions of Chinese cities. Street is a higher level administrative unit of community, and each street contains several communities. Similar to the former study, each trajectory can be represented as a sequence of street IDs and a sequence of community IDs. We also constructed corresponding activity sequences for all individuals. Since training a GAN structured model is very time-consuming, in this study, we used the trajectory data of only 2 days. So the length of the sequence is 48. So specifically, the trajectory generation GAN comprises two components, a generator and a discriminator. The generator is responsible for producing synthetic trajectories that closely mimic the distribution of the real data. We designed 3 generation tasks, the activity sequence generation task and the multi-scale trajectory generation tasks at both street level and community level. The trajectory generation task at community level is the main task, while the other 2 can be seen as auxiliary tasks. 3 tasks are executed sequentially. The activity sequence generation task enables the model to capture the temporal patterns of human daily activities, while the multi-scale trajectory generation task aids in capturing the spatial distribution of human movements. The generator takes 4 types of input: time ID, activity type, street ID, and community ID. Then those input data are passed through an embedding layer to create vector representations. The vector represented data are subsequently merged and fed into 3 separate transformer encoders to extract specific data features required for various generation tasks based on multi-layer perceptron. We expect the design of the auxiliary tasks have the function of improving the trajectory generation performance by introducing spatial temporal constraints. And we employed a convolutional neural network as the discriminator. The role of the discriminator is to determine the authenticity of the trajectory data. It is essentially a binary classification task to distinguish between the real and the generated sequences. And here is the complete structure of our proposed trajectory generation GAN, which also illustrates the adversarial training process of the generator. So in the generator, the trajectory is generated point by point. However, the discriminator can only assess a complete sequence. To evaluate each newly generated trajectory point, we employed a Monte Carlo search to complete the trajectory and repeated this process n times. So we can obtain n completed trajectories. Then we fit those trajectories into the discriminator to evaluate the non-authenticity of the generated trajectories. The evaluation result of the discriminator is called GAN loss, indicating the quality of this trajectory generation step. And furthermore, since we designed multiple scale trajectory generation tasks in the generator, we introduced a spatial consistency loss to measure the spatial inconsistency of generated data across different spatial scales. Specifically, we sampled trajectories generated from the current generator and check each trajectory if the generated community by the third task is within the generated street by the second task. Then the proportion of inconsistencies is used as the spatial consistency loss, which can reinforce the spatial constraints to make the generated trajectories adhering to the distribution of the real data. So to demonstrate the effectiveness of our approach, we compared it with 4 baselines using evaluation metrics similar to the former. And we can see that the proposed trajectory generation GAN outperforms the baselines in 5 of those metrics, with the only exception being its second ranking place to diatrust in the duration metric. Generally, it appears that the trajectory generation GAN exhibits better performance, producing trajectories that closely aligns with the distribution of real-world data. To validate the effectiveness of our model design, we conducted 2 ablation experiments. In the first ablation experiment, we kept the trajectory generation tasks at multiple spatial scales and removed the activity sequence generation task. And in the second ablation experiment, we kept the activity sequence generation task and the trajectory generation task at only community level and removed the trajectory generation task at street level. Accordingly, the spatial consistency loss in the training process was also removed. The results shown in the table indicate that the complete model outperforms the other 2 models in all metrics, proving the effectiveness of our model design. And we can now provide a summary of the trajectory generation GAN method proposed in the study. Firstly, we designed a generator with multiple generation tasks. The activity sequence generation task makes a temporal constraint on the generation process, which can help the model generate trajectories aligned with the temporal patterns of human daily activities. Secondly, we conducted trajectory generation tasks at both street level and community level, and designed a spatial consistency loss to make a spatial constraint on the multi-scale generation process, which can help generate trajectories aligned with the spatial distribution of the real data. So here comes to the conclusion. Today I introduced two trajectory generation methods, both coupling machine learning and mechanistic models on mechanisms. The activity to location combines machine learning and mechanistic models in a cascading way, while the trajectory generation GAN is a mechanism-guided learning model. Both approaches offer new insights on knowledge-driven or knowledge-guided GeoAI models for human mobility modeling. And here we also indicate some challenges and field directions on trajectory generation research. As the first one is exploring and revealing the underlying mechanisms of human mobility behavior from a multidisciplinary perspective. The second one is designing hybrid approaches by coupling machine learning and mechanistic models. The third one is leveraging cutting-edge generative artificial intelligence and even the large language model technologies. The fourth one is improving the model's spatial generalization and transfer learning capabilities. And the fifth one is controlling the cost of model design, the model training and implementation. And finally is designing a reasonable evaluation matrix and balancing data utility with the privacy-preserving effectiveness. Actually, human mobility is a typical human and environment interaction process. We think that research in geoscience can integrate with the theories and technologies from other disciplines, such as computer science, statistical physics, complexity science, transportation, and others. While on the other hand, we should harness the unique characteristics of GeoScience by explicitly incorporating geographic spatial effects such as spatial dependency, distance decay, spatial heterogeneity, scale, and more into the modeling process to enhance the rationality and the performance of the human mobility models. So this concludes my talk for today. Thank you all, and I welcome any question you may have.